Hi there, MG5004 DE5418. This is topic 5. This is class 1 where we're looking at trig functions. Quite a lot of this you will know, and so it will just be revision. You really need to know these definitions, and it's better to learn them in terms of adjacent, opposite, and so on, rather than in terms of ABC, but just for the moment I will write them in terms of ABC. And let's look at theta. Theta is the angle BCA. So just note that if the angle is called capital C, then the side opposite is called little c. So sine of theta is going to be C over A. Cosine of theta is going to be B over A. Tan of theta is going to be C over B. And we can also write that as sine of theta over cos of theta. Cosec theta is 1 over sine theta, so that's A over C. Secant of theta is 1 over cos theta. And cotangent is B over C, which is 1 over tan theta. And if you want a way of remembering that, if you want a mnemonic to remember that, it's SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. It's a good idea if you remember these two basic triangles, an isosceles triangle 1, 1, root 2, which has two 45-degree angles, and the other one that has angles 30, 60, 90, because it means then if you learn these, it's just quicker to remember. So also, if you remember that 45 degrees is also known as pi by 4, 30 degrees is also known as pi by 6, and 60 degrees is also known as pi by 3. If your triangle is not a right angle triangle, then if we need to find the lengths or the angles, we have to use either the sine or the cosine rule. The sine rule says that little a over sine capital A equals little b over sine capital B equals little c over sine capital C. And if you're going to use the cosine rule, a squared equals b squared plus c squared minus 2bc cos A. And remember, with the cosine rule, it's the same pattern, b squared equals a squared plus c squared minus 2ac cos b, etc. I'll do this example in class. So do this one in class. This is where you're looking at a mural which is 4 meters high and it's 2 meters above the observer's eye level, and you're asked to find the optimal distance away from the wall where the mural is hanging. But I'll do that one in class as well. You may well have heard of radians. So what's a radian? Why do we use radians? We use them because it makes calculus a lot easier. But what is a radian? And in case you've not been told or you've forgotten, that if we've got a circle and we've got a radius there, if we were to take that length and run it round the outside so that that length is also r, then the angle that that makes, theta, is 1 radian. And so some things kind of come from that. We get that 180 degrees is equal to pi radians. And the arc length that's drawn in there from A to B, the arc length is r times theta, but only if theta is in radians. And if we're looking at the area of a sector, then again, if theta is in radians, we can work that out. as r squared theta. So all of those work if the angle is measured in radians. It doesn't work, the formulas are not true if the angle is in degrees. And the same for calculus, it works nice and neatly if the angle we're talking about is in radians. If we work with a circle that's got a radius of 1, then we talk about the unit circle. And remember that sine of x is equal to the opposite over hypotenuse. So in this case, the sine of x is np over 1, or just plain np. If we rotate round the circle going anti-clockwise, as we're going round the circle that way, at least till upright, then np gets longer. As we go round to the next quadrant, to 180 or pi, np starts to get shorter again. As we go around in the third quadrant, np starts to get longer, but it's negatively longer. And then as we go back to the origin again, np starts to get smaller. So that's what if we were to graph against the angles x, what we would get is if we had np graphed against x, with x on the horizontal and np up there, what we would have drawn out was our sine curve. Because when we start at the beginning there, then the height, np, is actually 0 because it's sitting on it. So we're starting at 0, and that's what we're getting there. And this height is 1 because it's the radius of this particular circle. Now we've just chosen that. We've chosen the radius to be 1 because it means we don't have to worry about the bottom line there. If you go onto the internet and search animated sine curve, you will see how it's generated, and it's quite clever. A lot of them are very, very clever. So this is not animated, but you can see there by measuring Pn and then graphing it against the angle x, you can see that you're just going to trace out the sine curve as you go through. I'm sure you already know that the sine curve goes on indefinitely to the right and to the left, and we talk about that as we can write that as sine of x plus 2 pi k, or sometimes 2 pi n. Just n is just a number, where n is 1, 2, and so on. What we are noticing there is that the period of this is 2 pi. It goes from 0 to 2 pi, and then it repeats itself. So it has a period of 2 pi. Similarly, we could take the horizontal measure and do the same thing. We could have a circle with a radius of 1, and we could look this time at the horizontal length, Pn, and draw that on a graph with x on the horizontal and that horizontal distance on the vertical axis, and we would get what we know as the cos curve. Similarly, we write that the cos curve is equal to, or it's the cos of x plus 2 pi k, or n, whatever, and again you can see that the cosine function is periodic. It has a period from 0 to 2 pi, and it's repeating itself again, so it has a period of 2 pi also. Just a couple of things to remember. That shouldn't say that should say minus. If we've got a right angle triangle, we've got x there, then the angle at the top would be x minus pi by 2. So the sine of x is going to be equal to the cosine of x minus pi by 2. And the cosine of x would be equal to the sine of x minus pi by 2. We can generate a tan curve in the same way. This time, remember, the tan of theta is either the opposite over the adjacent or the sine over the cosine. And again, it's periodic, but this time remember the period is only pi. It repeats itself every pi. So from 0 to pi, and then from pi to 2 pi, and so on. And just another little thing, remember that tan of negative x is equal to negative tan of x. Got a lot to remember. Circular functions, trig functions, everything's all happening at the same time. We are going anti-clockwise, and we just work with the acute angle. If we're talking about cos of 135, for example, it's 135 is the same as 45. It's the same as 180 minus 135. So just thinking there that in the first quadrant, everything is positive. That's what it's got down here. In the first quadrant, everything is positive. In the second quadrant, cosine is negative. So the cosine of 135 is going to be equal to negative cos of 45. And you can look that up on your calculator. Similarly, if we were looking at sine 330, 330 goes all the way around to about there, and that angle there must be 30. So we could go backwards and say that sine 330 is equal to negative sine 30. Just remember that when we're talking about these acute angles, we're talking in the butterfly shape. We're talking off the x-axis each time. So each time we talk about the angle, it's in here. We don't take these angles. We don't talk about the red ones. We talk about the butterfly angles as being the acute angles that we talk about. So just as a reminder, sine theta is periodic with 360 degrees. That should say n in there. And cosine is periodic with a period of 360 degrees, and tan is periodic with a period of 180 degrees. So something like cosine of beta plus 500. What's 500 take away 360? So it would be equal to cosine of beta plus 140. In this diagram here, if you look at the solid curve is B, where we've got sine t. Now the top one is 2 sine of t, and what that is, that changes its height. And we call it the amplitude. So it's still going around sine t, it's still the same period, so it's still got the period of 2 pi, but now it's got an amplitude of 2. Similarly for C, graph C is the dashed one here, this is C. It only has an amplitude of 1/2, so if you look at that, it only goes up to 1/2 and down to negative 1/2. Now, our curves are not always going to go round with a period of 2. If we've got something like y equals sine 2t, that's going round twice as fast. It's going round 2 times in 2 pi. So the period, or p or t, whatever you want to call it, is now going to be 2 pi divided by 2. It was 2 pi, But now we're going around twice as fast. We're going around 2 times in 2 pi, so it must be pi. So the period then for sine 2t is pi. Note several things in this one. We've got time on the horizontal. Time is usually in seconds. And if we think about this, and if we write it in general terms, if we put in an amplitude as well, we're rotating round. We're rotating round at omega radians per second. And this is where we get the omega t must be equal to 2 pi, and t is equal to 2 pi over omega. This is the period. Now, in 1 second, remember we're talking about the radius. Oops, that's not a very good circle. We're talking about the radius of a circle. So the arm, if you like, is going round. In 1 second, this is going to make omega over 2 pi revolutions. And we talk about this as the frequency. If you look at that, that's just the inverse of that. Don't forget, we're talking radians here. If we're in time, we're going to talk radians. So let's have a look at B. Y equals sine 2t. So the time period for that is going to be 2 pi over 2, which is pi radians. So that's going to go around once in pi radians. And if you can see in the diagram, it does. If you look at C, C is y equals sine a half t. The time period there is going to be 2 pi over a half, which is 4 pi. So it's going to take 4 pi radians to go round once. And you can see that in the diagram. The dash dot graph will take 4 pi to go around once, 4 pi radians, 4 pi seconds in this particular case, to go around once. The curve in this example, not only has it got an amplitude and an angular velocity, but now it's got a shift as well. And the easiest way to do this is to draw the unshifted, so kind of forget about that for the minute, and then shift it once we've drawn it. So what we can do is we can rewrite this as y equals 3 sine. Now let's take omega out the front and write it like that. And this bit ends up to be our time shift, or our phase time. Our time shift. And the shift that we started with is actually the angular shift, or the shift angle. But once we've divided it by the 2 in this case, it becomes the time shift. Now, thinking about translations, as we will in a minute, just start thinking that a positive translation, a positive shift, actually goes to the left. Okay, let's draw the unshifted one for the moment. So let's just forget about that for the moment, and let's just draw y equals 3 sine 2t. So it's going to have an amplitude of 3. T is going to be 2 pi over 2, which is pi. Now we need to divide pi into 4. Because our sine curve has a peak, a 0, a trough, and a 0. Now that is just the curve of 3 sine 2t. What we're going to do is we're going to shift it. And if we talk about this, you can use a formula for it, the phase shift or the time shift is going to be alpha, which is that, over omega. And it's going to go that many units left if alpha is positive. So this is a rule that really sorts out which way you're going, left or right. Or it goes to the right by the absolute value of alpha over omega if alpha, what do I want to say, it moves that many units to the right if alpha is negative. Now in this case, alpha is positive, pi over 3, that's positive, so we're going to use a left shift. So every little bit is going to move over pi by 6. Every little bit. So the whole curve, the one that I've dotted, is going to shift pi by 6 to the left. Right, so we had pi by 3 divided by 2 equals pi by 6. Or we could look at the factorized version over here. So every point is going to go pi by 6 to the left, so it's going to go to about there, 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 and there. Join it up. And we're done. Again, we can see the time period just the same. It's just moved this distance here is pi by 6. So this point here is negative pi by 6. And we could find the point where it crosses the vertical axis. That's when t equals 0. So we could put that into our calculators and find that we could find that that intercept is about 2.59, 2.6. 2.6. So my drawing's not very good. This is the graph that we'll generate from the preceding slide, and I'll show you how to do that in class as well. Okay, there's lots of rules that govern trigonometry. These are some of the trig identities. There are more and more and more. There are lots. There are books full of them. You're not expected to learn all of them, obviously, but these are a few that you might find useful. But wait, there's more. There's some more trig identities. Again, the ones that you will need, you will be given, so you don't need to worry about that. It is good to learn a few, but if you're not the sort of person that can learn things quickly or easily, then don't worry about that. You can just look them up.